A square sign is attached to a round pole. Approximate the maximum moment that must be resisted by the base for a wind speed of 100 feet per second. So let's take a look at this. I have the ground, I have my pole, I have my sign on top of the pole, I have a free stream wind of 100 feet per second. That's going to cause a drag force on the sign. It's going to cause a drag force on the pole. And if we do a free body diagram of this, what that means is we're going to have a moment that's trying to resist all of this. So we have to do a mechanics equation to calculate this out. So I'm going to need to know what the force of drag at the sign is. I'm going to need the force of drag on the pole, composite body drag. We can just add the drags together to get the overall drag. And I will need this distance to 2, this distance to 1. Now the drag force, since it is by a wind pressure, it's going to be basically a distributed load. And so just like in mechanics, any distributed load is going to be placed at the centroid of the body. And so these ones are easy. We've got we've got a cylinder, we've got a sign, not a problem. And then we have to calculate out what the drag force is. So to calculate out the drag force, we're going to use our equation. Coefficient of drag is equal to the drag divided by rho over 2 v squared a star. Now, a couple things. One, we're going to have to look up in our textbook what the coefficient of drag for these shapes are, and we're going to have to determine which area that we're going to use. So we're not using the wetted area because we don't have a ship or a blimp. We are not using the planform area because these are not streamlined bodies. We will be using the frontal area. So if I look up the sign, which is going to be a rectangle, coefficient of drag in our book is going to say a rectangle is about a 1.1. So I'm going to rearrange this equation. So my drag force for 1 is going to be my coefficient of drag times rho over 2 v squared frontal area. Okay, so my coefficient of drag is 1.1. I have wind. I have to look up what the density of air is, and we're going to use 0.0024 slugs per cubic feet. And divide that by 2. And then we have our frontal area of the sign, and that sign is 10 by 10, so that's going to be 10 foot squared, multiplied by our speed of 100 feet per second, which is about 60 miles an hour or so. Or is it 100 miles an hour? I think it's 60 miles an hour. Multiply that together, and the drag force on the sign itself is going to be 1,320 pounds of force. Okay, now let's do the pole. So if I go and I look up a cylinder, because that's what I have here, we'll find the coefficient of drag is about 0.8. Now we're going to do the same thing. Drag on the pole, which is the drag of 2, is going to be the coefficient of drag, so 0.8. Same density of fluid. Same velocity. And I just noticed that I forgot to, I wasn't going through my units. That is actually squared because it's velocity squared. Now the frontal area. Now we have a cylinder, but we need the frontal area. It's the 2D projection. And that cylinder is 60 foot tall by 1 foot wide because we're going to have a rectangle. And so then if I do that, my pole is going to have 576 pounds of drag. Fluid mechanics is done. Now it's time to go into mechanics of materials. Going to have to calculate out that moment. Because if we go back here, we're going to have, if we do the sum of the moments is equal to 0, we'll say counterclockwise is positive. That's going to be FD1 times D1 positive plus FD2 times D2 minus the moment at the base, which is what we're trying to find. So if I rearrange that equation, it's the moment of the base is going to be FD1 times d1 plus fd2 times d2. And so the drag force at 1 is going to be our 1320 pound. So where do we apply that force? We apply that at the centroid of the sign, which is going to be right here, which is 5 feet from the base of the sign, plus the 65 feet to the ground, because we have to go all the way back to where that moment is. And so we've got 65 feet. And then we're going to add to that the moment of the second drag, 576 pounds. The location of that centroid's right at 30 feet. And so, if I put all that together, the moment is going to be 103,080 pounds. 80 pound-feet, or foot-pounds. That is the moment that we will have to resist at the base of the sign at that wind velocity.